going to talk about slice categories, and that's going to lead us to talking about comma categories. Now, comma categories are one of those things that people get very upset about because they think a comma category is a silly term, and it actually grew up by mistake because they hadn't thought of a notation for it and they were just using commas, or maybe the commas were their notation, they hadn't found a word for it, so they just referred to it by comma and then it sort of stuck. But never mind, we shall plough on and use the terminology anyway. So first of all, what's a slice category? Given a category C, we can kind of slice it over some object in C. So we fix an object, X in C, then we can form this slice category. Then we have C sliced over X, which has the following objects. So the objects of this category are pairs, an object in A together with a morphism down to X. So it's pairs A, P, like that. And then what's a morphism? Well, the morphisms are just exactly the morphisms they simply have to be. And you can see how categorically you're thinking now by seeing if you can invent what these morphisms are while I'm writing them on the board. So let's see, the morphisms. So we have to think about morphisms from a pair AP to a pair A prime B prime. So if we just write out what that data is, it's A with a morphism down to X, and it's A primed with a morphism P prime down to X. So what could a morphism from here to here possibly be? Well, yes, it's going to be a morphism from A to A prime such that this triangle commutes. So the morphisms are F from there to there such that this triangle commutes. Now, there's also something else which is a co-slice category, or a slice under. So now we can take our object and put our category kind of under it, and it's the dual of this. So now you can do all that yourself, I suppose, if you want to. The objects, now the X is going to be at the top and the morphism is going in that direction, and the morphisms are, well, what's the data going to be? We're going to have one pair AP like that, we're going to have another pair A prime P prime like that. So this time the morphisms are going to be in that direction, making this triangle commute. So why am I telling you about this? Well, one of the things I felt like saying was talking about products in this category. So let's just take this part of the definition off. Actually, you know what? Before I say that, I should point something out, which is that if C has a terminal object, then if you slice yourself over your terminal object, nothing's going to happen, right? So C sliced over the terminal object is just the same as C, because the objects are going to be pairs, an object together with a morphism down to the terminal object. But there is only one morphism to the terminal object from any object. And so asking for a morphism down to the terminal object is no further information whatsoever from just having the objects in the first place. So you don't get anywhere by doing that. And dually, if C has an initial object, 0, then, well, the dual result is true, which is that if you slice under 0, then you don't get anywhere. Right, okay, so what was I going to say about products? What I want to show is that products in this slice category are the same as, well, as the same as what, I wonder. So let's think about products. A product in this slice category. Well, what's it going to be? So here's x. Everything lives over x, so we're just going to sort of put that on the board. Perhaps I'll put it in blue, because this x just isn't going to move. Okay? Now, what do we take products of? Or rather, of what do we take products? We take them of two objects in our category. So let's put up two objects in our category. Here's A, with a map going down to here, which I'll call P, and here's, and that's a terrible letter for it, S, and B, with a map going down to it, which I'll call T. Is this beginning to look familiar? What do you think could possibly happen when I take a product of this? Well, what's a product going to be? It's going to be an object of our category, of our slice category, together with projections down to the two objects we're taking a product of, with some universal property. So let's start by writing up an object. Okay. So an object is going to be some object, let's call it C. And because it's a morphism in an object in the slice category, it's got to come equipped with a morphism down to X, like this. Right? So that's the object. Let's call that P. And it's got to have projection maps as well. So it's got to have a projection map here. And because it's a morphism in the slice category, it means that this triangle has to commute. And we can call that, oh, that was terrible notation as well. I'll call that U for universal. Because usually our projection maps are called P and Q. So if we were going to write this in the non-geometrically intuitive way, we would write our pairs A, S. Here are the things we're taking product of. Here's our pair B, T. I don't really leave myself enough space, do I? Here's A, S, here's B, T, and here's the vertex C, U. And here's the map P that makes that triangle commute, and here's the map Q that makes this triangle commute. And so what we want is we want to say what the universal property for this product is, which is to say that given some other V, comma, that's enough letters of the alphabet, F, together with maps going like this, there's got to be a unique factorization down here. So what's that going to say? Here's V equipped with its map going down to here, and it's got to have also a morphism here and a morphism here. Then we've got to have a unique factorization like that. Now it should start looking a bit like a pullback to you now, because if you just ignore these things coming down the diagonals, we've got a square here, and our universal property looks quite a lot like the universal property for a pullback. We just have to make sure that this really is a pullback. So let's think about it a bit harder. Does this square commute? Well, yes it does, because this triangle commutes with the U thing, and this triangle commutes as well, which means that the square commutes. And likewise, the universal condition says, given anything up here equipped with a map down to here, and a map here such that this triangle commutes. Now, because this map coming down here is just the composite of this and this, we could just not bother writing it and understand that it had to be that composite, right? And because this map coming down here had to be the composite of this and this, we can just not write that one as well and understand that what it was kind of there for was to assert that this square commuted. So this one asserted that the inside square commuted, the one from V down to here asserted that the outside square commuted, and then the factorization here, we know that it's got to be a morphism in our slice category. And what does that mean? That means that all the triangles in sight have to commute. So we could write that out very slowly and show that the universal conditions really are the same. So when you're checking that some limit is the same as some other limit, you really have to check that the exists unique conditions are the same. And here, I hope that I've convinced you that that's going to be the same. The dual result, then, is that co-products in the slice under are the same as push-outs in the place that you started in. Today we're going to talk about comma categories. Comma categories are a generalization of slice categories that we did last time, or rather slice categories are a special case of comma categories. Anyway, remember that when we did comma categories, we started with a category C and an object X in C, and then we could either form the slice over x with a slice under x. Now this time we're going to just soup it up a little bit, and we're going to start with a functor, f from c to d. And this time what we're going to do is we're going to fix, so we fix this, and an object x in d. And what we're going to form, instead of slicing d over x, it's going to be called f down to x. Because the objects this time are going to be, they're going to be a bit like before, but a little bit more complicated. So x is still going to sit here at the bottom, and we're still going to have a morphism down to it, but it's not going to be any old morphism this time. It's got to be f of something, f of, let's call it c. Okay, so it's a pair which is c in the category c, and a morphism p, morphism from f of c to x. So your data, part of your data is something in c and part of your data is something in d, right? So now what's a morphism going to be? Well, let's write down what two of these things look like. So here's our x at the bottom that stays fixed. Perhaps I'll put it in blue again. This x at the bottom stays fixed. And we've got an f of c, and we've got an f of c prime, and morphisms going down to x. And so you might think that, as before, a morphism should be a morphism like that, making this triangle commute. But we have to be a little bit careful. It's not any old morphism from here to here, because, of course, think of our data that we started with. An object is an object in C and a morphism going down here. So a morphism really ought to be a morphism in C together with some condition. So, of course, what it's going to be is a morphism from C to C prime, such that f of it makes this triangle commute. So what it is it's f from C to C prime in the category C, such that that triangle commutes. And the dual case for this is that we can take x going down to f, and what that has is objects. It's just all the other way up. You can all do this. I don't know why I'm doing it for you. Let's see, so x is up there, and we have f of c at the bottom. So now the objects are a c in c and a morphism p from x to f of c, and of course a morphism in this category is going to be something that makes the triangle the other way up commute. Here's p, here's p prime, and here's f of f. So it's going to be a morphism f from C to C prime, such that this triangle commutes. Now, one of the reasons I'm particularly fond of these common categories is that they give us a very nice way of talking about adjunctions. But I'm going to leave that for now and plow on to an even further generalization of this common category, which is that if we fix this functor but not the object x in D, then we can do a further kind of common category, which is that we can slice this category down to f. So now the objects are going to be I have the other one on this side, didn't I? F down to D. So now the object is still going to look like this, except that our object x at the bottom isn't fixed anymore. So now the data is C in C, x in D, and the morphism P. Okay, so now what are morphisms going to be here? Well, if you look at the data for an object, it's an object here, and a morphism. So a morphism between them should be a morphism here, and a commuting condition. Okay, so let's write down what our two objects are. Here's one of them, and here's another of them. And let's think about what a morphism from here to here could possibly be. I'm going to draw it in orange. Well, of course, it's got to be a morphism down here, which I will call G. And it's got to be a morphism up here, and just like before, it has to be f of something. So let's call that f of f, and this square has to commute. So let's what are we going to do? Oh yeah, it's f from C to C primed, which corresponds to the object in C. We've got g from x to x prime, and we've got such that this commutes. So you can see that there's a sort of dimension shift that's going on. Whenever you look at morphisms between these objects, everything kind of shifts up a dimension. So this object becomes a morphism, this object becomes a morphism, and this morphism becomes a commuting condition. Of course, if we were in a higher dimensional situation, then this one cell would become a two cell, and then if there were any two cells here, those would become commuting conditions. Anyway, I'm rather jumping ahead of myself. Of course, there's also the dual to this, but I think you can probably all work out the dual to this, which would be d down to f. I just want to do the one even further generalization of the comma category situation, where you start with two functors, f and g, and you can form f going down to g. So what's that going to be? Well, now it's going to look like f of c, I don't like my notation anymore, going down to g of, well, what's an object of E going to be called? I think this has got confusing. I'm going to use little letters now. F of C and G of E. So E is an object of E, C is an object of C, and then there's this morphism in D. So we've got three things. We've got C in C, we've got E in E, and we've got P, this morphism in, so it's a morphism in D. So now, what's a morphism in this category going to be called? So that's the objects. The morphisms, like over here, they want to be squares, and we want to have one morphism in C for this part, one morphism in E, and the commuting condition. So this shouldn't be very difficult anymore. Here's what one of our objects is, P. Here's our other object, P primed. Here's f of a morphism, f of something, f. Here's g of something, which, now I really hate my notation, but I'm going to just grit my teeth and call it g. So it's going to be, it's a morphism P from C to C primed. It's a morphism, no it's not, a morphism is a morphism F from C to C primed, a morphism G from E to E primed, such that all of this lot commutes. Now, I hope that with all of these slice and comma category conditions, you can see that given the data we started with, we sort of made what was a sensible category out of them. We kind of constructed this category. It might have seemed a bit funny at first, but there wasn't anything very arbitrary. There was nothing arbitrary about how we made these morphisms. It was completely obvious how these morphisms should be. And you should start thinking to yourself now that things like that, where if you feel that you don't have any choice, if you feel that there's some non-free will going on, that there's some kind of universal property. And next time we'll see that all of these constructions are, in fact, they do have universal properties, and they are some kind of limit and co-limit, albeit in a much more complicated kind of way.